So in this video, I'm going to show you how to input data into the TI83, 84 family of calculators and how to create scatter diagrams, best lines of best fit, compute correlation coefficients and coefficients of determination, as well as use those lines to make predictions about data. So first off, if I want to put in my data into my list, I first need to figure out which one's the independent and dependent variable in the data set. In this case, we're going to let the independent variable be the temperature, and I'm going to let the dependent variable be the chirps, because the chirps depend on whatever the temperature is. I can infer this from what they said up here in the data. It says, perhaps you've noticed the number of chirps seems to increase with the temperature. So the temperature is not dependent on the number of chirps that a cricket has, because the temperature is going to stay whatever it's going to be no matter what, but the chirps will change based on the temperature. There's a little tongue-tie in there. So I'm going to put this into a scatter diagram of data. So before I do that, what I want to do is turn my diagnostics on so that I can do the next step, which is compute the linear correlation coefficient. So if you go to second 0, you only have to do this one time. So once we've done this for the first data set, you shouldn't have to do it anymore after this. Some of you may already have your diagnostics on. I'm going to hit alpha D just to go right to it. From when you were in high school. But some of you may have to, turn it on as we go here. But like I said, if you turn it on in high school, it's probably still on, or whatever previous math class you had. Alright, so I'm going to get pretty close to it here. You're going to see two diagnostics. You're going to see diagnostic off and diagnostic on. We want diagnostics on. There it is, diagnostics on. So I'm going to hit enter there and just hit enter, and it should say done to make sure that it's done. Alright, so now I'm going to go to stat, edit, and I'm going to type in my data. So I'm going to clear out whatever's in there. So just go up, highlight it, hit clear and enter. And we're going to enter all of our data into list L1 and L2. Make sure if you clear a list, you do hit the word clear and not delete. If you hit delete, it's going to get rid of the list, but we need that L1 and L2. That's where our data is going to go. So L1 is going to be your independent variable. In this case, it's going to be the temperatures. And notice how this is 4 columns, but really this data goes with this data. The first and third column go together. Second and fourth go together. It's just put there so that I can see it easier. So don't think about this as 4 columns. These are all the temperatures. These are all the chirps. All right. So I'm going to type the data in there. Alright, so I went ahead and did it all. So I put all the data in. It does not hurt to go and check and make sure that you have the correct data. So in all of L1 is all my temperature values. All of L2 is all my chirps. I already went back and double checked and made sure I had the data right. And sure enough, I did have a data point wrong. Not wrong, just, it was entered in there and it shouldn't have been. So I have all my data points in there now. So the first thing it wants me to do is draw a scatter diagram of the data. So to do that, I go to second y equals, which has the stat plot above it. And I want to turn my plot on. So I'm going to hit enter here. And I'm going to make sure on is highlighted. I'm going to hit enter to make sure that it's on. If it's hovered over off, then it's not going to appear. And then I'm going to go down to type and make sure that the scatter diagram is chosen. By default, your calculator chooses a scatter diagram. If you may have been doing something else, you might have a histogram or something label, but you want to make sure that scatter diagram is chosen. The X list is your independent variable, which in our case is L1, and then the Y list is your dependent variable, which is L2. This again will default to L1 and L2, but you want to double check and make sure that they are that way when you are trying to find your scatter diagram. These are just the marks. You can either have like a little square, a plus sign, or a dot. I'll leave it here on the default. That's just so that you can see the visual of it. If I hit graph, I probably won't see anything. No, because this scale is from -10 to 10. And you can see here none of my values fall between 10 and 10. So what I'm going to do is hit zoom stat, which is number 9, to make sure that my window is appropriately sized so I can see it. So I'm going to hit zoom 9. You can just type 9 as well. And there I have my scatter diagram. That's a nice diagram. So if we look there, it has a positive correlation for sure. We can actually figure out the linear correlation coefficient to see how strong it is. So that's number 3 here. So let's find the linear correlation coefficient. So to do that, I'm going to go to Stat, over to Calc, and there's actually 2 options here. I can do linear regression. There's another one that says regression linear. I'm going to do number 4 here. So I'm going to hit number 4. Make sure my X list is L1, Y list is L2. The frequency list, we're not going to worry about that. We can store the regression equation. I'm not going to choose this because not all your calculators have that, so I'm not going to choose it. And then I hit calculate. Okay. So the linear correlation coefficient is R. So in this case, R equals 0. I'm going to do 4 decimal places, 8351, which is pretty big. Like we've said, the closer R is to 1, then we can say that that line is going to be pretty close to a straight line, or a line where all the data points would fall onto it. So 0.8351 is pretty close to 1, so I would say that a linear relationship does exist between temperatures and chirps per second. Now the line of best fit, you can see up here they make it really straightforward. They have y equals ax plus b. A is your slope and b is the y-intercept. So I'm going to write the equation just like that. It's going to be y equals a, which is 0.2, I'm going to use 4 decimal places, x plus b. Now b in this case is negative, so it's going to end up being minus 0.3091. So this is my line of best fit. Now I'm going to actually put that line into y equals so y'all can see what it looks like. So I'm going to type in 0.2119x. Now you can type, there's a way that you can just store the equation and put it in. I'm just going to show you this way because all calculators will do it. And if I hit graph, you should see a nice line going through this data, and we can. So you see here that the line actually hits. It looks like 4 or 5 data points. Not all of them fit on there, of course, because the regression is not exactly 1. But since it's pretty close, we can say that it's almost, it is a line best fit, and it's very linear. So the slope here is the number in front of x in this case is 0.2119, and the y-intercept is negative 0.3091. And it says interpret them if appropriate. So the slope is the change in the dependent variables over the independent variables. So this says for every 1 degree change in temperature, the number of chirps goes up 0.2119. And I say it goes up because 0.2119 is positive. If it were negative, then that would imply that the chirps were going down. But this is for every 1 degree change in temperature, the number of chirps goes up to 0.2119. Now the y-intercept is telling us what the value is at 0. So the y-intercept says when the temperature is 0 degrees, we can expect to hear negative 0.3091 chirps. Now, is that appropriate? That's not appropriate because we would not be able to hear negative number of chirps. That's going to always be a positive value. So here that y-intercept has to be there for creating the line, but it's not always necessary in the interpretation of the problem. So here, the y-intercept is not appropriate to interpret. Now, if I want to predict the chirps per second if it's 83.3 degrees outside, well, that just means I'm letting x equal 83.3 because that's the independent variable. So what you can do is just plug it in here. 0.2119 times 83.3 minus 0.3091. You can do that, or if you go back to your calculator, I can just go to second calc, and I can find the value of 83.3 and just type it in here, and you'll get the same thing. You actually get a more accurate answer using the calculator because it has not rounded anything. I'm going to round to 1 decimal place for the y because all the numbers in my table are 1 decimal place. So it's 17.3 chirps per second. Alright. A cricket chirps 15 times per second when the temperature is 82 degrees. Is this rate of chirping above or below average at this temperature? Alright, so let's find out what the average is at x equals 82 degrees. So I'm going to just go back over here, and I'm going to type in 82 to figure out what it is. So 82 degrees, y equals 17.1. So if we know that the cricket chirps 15 times per second during that temperature, and our line predicts at 17, then 15 is below 17. So I would say that's below average at this temperature. I see number 9 here says it's 55 degrees outside. Would you recommend using the line of best fit to predict the temperature of the chirps per second of a cricket? So 55 degrees is going to be outside of our range of these numbers because, let's see, the lowest number we had on this list looks like 69.4. So this is going to be outside of our range of numbers. So this is extrapolation because we're going outside of our data set. Whereas this one above, when we were looking at 83 degrees, was interpolation, as we were inside the data set, because our highest point was 93.3, and we were inside of that. So we can see what it looks like. We could try to use it. More often than not, we try not to use extrapolation. We don't like to go outside of the bounds of our data set, but it may actually give us the right answer here. So let's see what the number of chirps is at x equals 55. I have a guess that it's not going to give us an answer we want. So when x equals 55, let me go back here, y equals, nothing, it won't do it. Now it won't do it here because my bounds are not there. So I can actually change that. Let me let my x, see my lower bound here for x is 67. Let me let it be 50. And then that way I can actually do it. So let me go back to the graph. That already is, guess number 1, and it's not going to work. So let me go to the graph and plug in 55. And I get 11.3. Well, could a cricket have 11.3 chirps per second? I would say it might could. Looking here at the numbers here, the number of chirps looks like 11 could be a plausible answer. So yeah, I guess we could use this line of best fit to predict the numbers. But again, we recommend you not going outside of the data points to use it as predicting numbers, just as a rule of thumb. All right, now r squared, let me go to r squared. I'm going to do a second quick and go back to my line. We had already got the correlation coefficient. I'm going to hit enter again just to get it. Oops. We got r to be 0.835. Now r squared is just taking r and squaring it. So r squared equals 0.6975. So what that tells us about the variation in the variables means that 69.75% of the variation in the temperature compared to the chirps per second can be explained by the line of best fit. Which implies that about 30% of the data must have something to do with outside variables that we have no idea about. There could be other things that affect chirps per second there. I would assume things such as humidity may affect chirps per second, time of night, time of day, that sort of thing. So there's other things that are unaccounted for there. Otherwise, we'd have 100% correlation coefficient determination, and that's just not so. So if you have more questions about these, let me know. There are plenty of examples of these to try. So try them and use these things in your calculator to try to find the scatter diagram, the line of best fit, correlation, coefficients, and coefficient determinations.